Hello, this screencast is the first in a series where we will look at transforming the sine and cosine functions. In this video, we will focus on how vertical stretches and shifts impact the amplitude, midline, period, and range of the sine and cosine functions. Recall our previous work where we studied how the graph of the function g, defined by g of x equals a times f of x minus b plus c, is related to the graph of f, where a, b, and c are real numbers with a not equal to 0. We saw that the real number b horizontally shifts the graph of f, the real number a vertically stretches the graph of f and reflects f over the x-axis when a is less than 0, and the real number c vertically shifts the graph of f. Because such transformations can shift and stretch a function, we are interested in understanding how we can use transformations of the sine and cosine functions to fit formulas to circular functions. Given the functions k of t equals a times the cosine of t plus c and h of t equals a times the sine of t plus c, we see that k of t and h of t are transformations of the cosine and sine functions respectively. As a result, the real number a will cause the cosine and sine graphs to be vertically stretched or reflect over the x-axis when a is less than 0, and the real number c will cause the cosine and sine graphs to be vertically shifted. This leads to the question, how do vertical stretches and shifts impact the amplitude, midline, period, and range of these functions? On the next slides, we will look at some examples to answer this question. But first, let's quickly recall the properties of the parent functions sine of t and cosine of t. Recall that the amplitude of 1 is the radius of the unit circle, the midline y equals 0 is the y-coordinate of the unit circle, center, and the period 2 pi is the circumference of the unit circle. Also notice that the range of the sine of t and the cosine of t is negative 1 to 1. Now, let's look at some cosine and sine functions that have been vertically stretched. On the left, we see the graph of k of t equals 3 times the cosine of t, and on the right, we see h of t equals 1/2 times the sine of t. Pause the video and take a moment to identify the characteristics listed on your screen for both functions. Alright, so in k of t equals 3 times the cosine of t, we observe that the amplitude is 3 and the midline is y equals 0. We also see that it takes an interval of length 2 pi to complete one cycle, so the period is 2 pi. Lastly, the range is negative 3 to 3. And for h of t equals 1/2 sine of t, we observe that the amplitude is 1/2 and the midline is y equals 0. We also see that it takes an interval of length 2 pi to complete one cycle, so the period is 2 pi. And lastly, the range is negative 1/2 to positive 1/2. If we compare the properties of these graphs to those of cosine of t and sine of t, we notice that vertically stretching the sine and cosine functions affected the amplitude and range of the graphs. Specifically, the factor by which the functions are vertically stretched is equal to the amplitude, and this impacts the range of the function as well. Now let's look at the impact of vertically shifting the cosine and sine functions. On the left, we see the graph of k of t equals cosine of t plus 2, and on the right, we see h of t equals the sine of t minus 1. Pause the video and take a moment to identify the characteristics listed on your screen for both functions. Alright, so in k of t equals cosine of t plus 2, we observe that the amplitude is 1 and the midline is y equals 2. We also see that it takes an interval of length 2 pi to complete one cycle, so the period is 2 pi. Lastly, the range is 1 to 3. And for h of t equals the sine of t minus 1, we observe that the amplitude is 1 and the midline is y equals negative 1. We also see that it takes an interval of length 2 pi to complete one cycle, so again, the period is 2 pi. Lastly, the range is negative 2 to 0. If we compare the properties of these graphs to those of cosine of t and sine of t, we notice that vertically shifting the sine and cosine functions affected the midline and range of the graphs. Specifically, when the graph is shifted up or down by a factor of c, the midline and range were shifted in the exact same manner. So now let's look at an example where we perform both a vertical stretch and a vertical shift to the graph of a circular function. Here we want to describe the graph of h of t equals 2 times the sine of t plus 3 as transformations of g of t equals the sine of t. In addition, state the amplitude, midline, period, and range of h of t. Pause the video and try to answer the question on your own. All right, so we know that the first transformation is a vertical stretch by a factor of 2. That means the amplitude will be 2. The next transformation is a shift up of 3 units. That means the midline is y equals 3. We saw that vertical stretches and shifts do not impact the period, so the period is still 2 pi. And we saw that both vertical stretches and vertical shifts impact the range. So it helps if we recall that half the curve lies above and half the curve lies below the midline of y equals 3. Given the amplitude of 2, we can conclude that the lowest output value the graph reaches is 3 minus 2, which equals 1, and the highest output value the graph reaches is 3 plus 2, which equals 5. So the range of this graph is 1 to 5. And here's a graph to confirm our findings. We can verify that the amplitude is 2, the midline is y equals 3, the period is still 2 pi, and the range is 1 to 5. Let's look at one more example. Describe how the function k of t, described below, is the result of transforming f of t equals cosine of t. In addition, state the amplitude, midline, period, and range of k of t and write a formula for k of t. Again, pause the video and try to answer this question on your own. All right, so in this case it helps to first identify the properties of the graph and then use those to describe the transformations. We notice that the midline is y equals -1 and the amplitude is 1/2. We also observe that the period is 2 pi and the range is -1.5 to -1/2. Since the amplitude is 1/2, we know the graph of cosine of t was vertically compressed by a factor of 1/2. Since the midline is y equals -1, we can conclude that the graph of cosine of t was vertically shifted down by 1 unit. We also need to remember that the cosine function normally has a maximum when t equals 0, but this graph has a minimum when t equals 0. This implies that the cosine of t was reflected over the x-axis. Putting together these transformations, we can conclude that a formula for k of t is -1/2 cosine of t minus 1. In conclusion, we saw that multiplying the cosine and sine functions by a factor of a applies a vertical stretch or a reflection across the x-axis when a is less than 0, and that a vertical stretch determines the amplitude of the transformed function. We also saw that adding the real number c to the cosine or sine functions applied a vertical shift, and that a vertical shift determines the midline of the transformed function. Lastly, by starting at the midline y equals c and subtracting the amplitude, we get the lower value of the range, and by adding the amplitude, we get the upper value for the range. In the next video, we will look at the effect of horizontal shifts on the graphs of the cosine and sine functions.